Thank you very much, Hugh, and thank you very much, Sir Stephen Dalton and Mrs. Dalton, for coming here tonight. I'm very, very honored. And good evening, distinguished guests and ladies and gentlemen. It's really a pleasure to be here, and I'm very honored to be given the opportunity to give the Gordon Core lecture here. Remembering Gordon, who was the creator of the Toulouse branch of the Royal Aeronautical Society Branch Toulouse. Now, the title that I've given to this presentation is Wings on Orbit, and I'm going to talk about the Space Shuttle. And of course, the lectures here are normally focusing on safety aspect and flight test aspects. I'll be broader than that. I'll talk about the Space Shuttle in general, because it's such an extraordinary vehicle compared to other airplane, any other airplane, even the most sophisticated and special. This gets out of the box completely in the world of aeronautics, having the capability to get outside of the Earth atmosphere and on low Earth orbit at 28,000 kilometers an hour, or about 8 kilometers per second, and then re-entering the atmosphere at Mach 26. You can imagine the heating that you have when you come back in the atmosphere at Mach 26. And finishing the mission with a glider type approach and landing on a runway at Kennedy Space Center, the launch site, or at another landing site. There were several landing sites in the US and also around the world to allow the landing of the Space Shuttle. An extraordinary vehicle, really. And for me, a huge privilege as an ESA astronaut. I was never a NASA astronaut, but an ESA astronaut, European Space Agency. An extraordinary privilege to have been able to accomplish 4 missions in the 90s, 92, 93, 96, and 99, including, for somebody who has been trained as an astrophysicist, the extraordinary opportunity to go on servicing the Hubble Space Telescope. These were the first servicing mission on one hand, which was the most critical because we had an optical problem, and then the third one, and this was for me extraordinary as an astrophysicist to go and touch Hubble with my gloved hands and to work on it and make it serviceable and useful. Because for the first 3 years before the optical correction, it was hardly able to get sharp pictures of an object in the universe, and it needed that repair. The second time I went, which is the third servicing mission, we had a problem with the capability of the telescope to maintain its accurate orientation in space, which is of course essential for an orbiting telescope. So again, I won't focus so much on flight testing and safety aspect. I will mention them, but I'll talk about the Space Shuttle, an extraordinary space vehicle. The outline of the presentation, I'll talk about the Space Shuttle project, how it was generated and when. In fact, it was at the end of the Apollo program. Americans were already thinking about the next program, big program, which was going to be winged reusable vehicle. Talk about preliminary studies that show the compromise I will mention, and the reality. There was the objective and the reality, in fact, were quite different. So that's going to be one of the big lessons. There were unbelievable thoughts about the utilization of the Space Shuttle, like a space airliner. That was the idea. Going for the crew members and all occupants in a shared safe environment, escape like an airliner. NASA regretted it afterwards, but that was the first idea. I remember the first pictures when I went there to Houston in 1980. We could see, this was before the first flight, which was in April 1981. You could see pictures of the shuttle coming back from flight in an orbital processing facility, open the payload bay doors, exchange the payload in a few days, and then off we go again. They were planning 24 flights minimum per year, It never happened, of course. So the thinking about the use of the Space Shuttle was extraordinarily ambitious, and it never really happened. I'll mention some highlights. I can't talk about 135 missions. There is no need to do that. But some highlights of especially the early missions of the Space Shuttle in the 80s. I'll say a few words about myself. That's not a me presentation today, although I went on the shuttle 4 times, but I'll mention briefly my 4 missions, especially the Hubble servicing mission. STS-46 was the first one in 92, 61 in 93, 75 in 96, and 103, just before the turn of the century in December 99. Conclusion at the end. Now, the shuttle project, it was initiated already during the Apollo program. You know, the Apollo program started in the 60s. The first flight to the moon, around the moon, was in December 1968. And the first landing on the moon, as you know very well, was in July 1969, Neil Armstrong and Buzz Aldrin. And then we had Apollo 12, 13, which, as you know, never reached the moon, but they could save the crew, which is a great achievement in itself. 14, 15, 16, 17. 17 was in December 72, and already before the end of the Apollo program, which was a remarkable program, it was really the highlight of the whole set of missions, of human missions in space. There's no doubt about that. Enormous success. But before the end of the Apollo program, NASA already and the aerospace industry worked on the next project, the Shuttle project. And the idea was to replace all of the launches for the DoD, the Department of Defense, commercial users, and for research and development purposes, NASA. NASA is a research agency. It had nothing to do with the military. DoD is a military, they have their space program, but the idea was to have the shuttle used for all these purposes. And the main goal, and read that carefully because this was the idea, was to offer frequent, and I put relatively here, relatively cheap access to low Earth orbit. When I use the word LEO, it's not a lion, but it's a low Earth orbit. For all users. I mentioned the DoD, the commercial users, and research and development run by NASA. This was the idea. And airline type operation. You come back from flight, landing on the 5-kilometer long runway at Kennedy Space Center, orbital processing facility. Within a week or 2, you go again, like airliners, and in shirt sleeve environment, like you all are here. No special suit. If you need to go spacewalking during the mission, of course, you need a spacesuit. But the mission was going to be with no special equipment for the crew, like airliner crews. Now, initially there were several concepts looked at with total reusability. Here you see one of these concepts where you have the first stage, which is winged vehicle with hydrogen-fueled engine here, but also air-breathing engines. And after separation of the second stage, which is like the orbiter that eventually was chosen, after separation, the first stage would come back and land on the runway, would be totally reusable. This was the orbiter part, this part here, that already has familiar shape, which was chosen later for the Space Shuttle orbiter. Now, this is an interesting graph which represents the cost per flight in $1 million, and this is development cost. If you have a totally reusable vehicle, the cost per flight is lower, but the development cost is much higher. And it would have been so high that it was not possible to do this. So they wanted to reduce the development cost, but it means that it was only a partial reusability, and of course the cost per flight was going to be higher. And that's an interesting curve because this is valid for any aviation or space program. you need a lot of development costs in order to reduce significantly the cost per flight. This was drawn by George Lowe, who is a NASA administrator in the past. Now, the compromise, low Earth orbit access for 7 crew members and payload about 20 metric ton, which is quite a lot. And the size of the payload bay and the capability in metric tons to orbit was determined by the Department of Defense needs. They wanted to have that capability. Eventually, it happened that it was very useful for commercial and science users. Typically, the Hubble Space Telescope could fit well in the payload bay and was at about that mass, a little lighter than that. But anyway, the DoD had the requirement for a large payload bay and a large mass to be brought to low Earth orbits. And eventually, we got only partial reusability. The external tank, which you see here, containing about 700 tons of metric tons of liquid oxygen, liquid hydrogen, to feed the main engines at the bottom of the orbiter, was jettisoned after main engine cutoff, 8.5 minutes after liftoff, and was lost. It fell down in the Pacific Ocean. And the solid rocket boosters, which you see here, which provided extra thrust for the initial ascent for the first 2 minutes, then they were jettisoned, separated and jettisoned, fell in the ocean. They were reusable, but there was a lot of maintenance needed to make them really reusable. So that was a compromise. And again, lower development cost than if it had been a completely reusable vehicle, but of course higher operational costs because of maintenance of the solid rocket boosters on one hand, the loss of the external tank. Now, I won't go into the detail of that, but this is the so-called orbiter of the Space Shuttle. The Space Shuttle is everything. It's the orbiter, which you see here, which has a cabin for 7 people, the large payload bay, again up to 20 ton, brought to low Earth orbits, and the external tank and the solid rocket boosters. This is the orbiter. And that's a part that was staying on orbits and then coming back down, gliding and landing on a runway at the end of the mission. And you see the bottom of the fuselage and the wings is covered with thermal protection tile. The black tiles, which are silicium tile with the glazing on top, are the ones that were able to take the highest temperature, because during the entry, the idea was to come with a high angle of attack, and the part of the vehicle exposed to the heat of reentry was the bottom of the fuselage, where the nose, of course, the leading edge of the wings, and the whole bottom of the fuselage and the wings. So the black tiles are for high temperature, and the white tiles and the rest, which is white, was covered with another type of thermal protection which was not designed for such high temperatures as the black tile. And a total of 6 orbiters were built. The very first one, Enterprise, was used for approach and landing tests. This was at the end of the 70s. Again, the first orbital flight of the shuttle was STS-1, was in April 1981, but in the late 70s, they used Enterprise on top of a Boeing 747 of NASA. The first flights were captive, and then they separated Enterprise. It was like the orbiters that were built for space, except you did not have the main engine, the shuttle main engine, the back of the orbiter on one hand, which made a big difference because this is a piece of very high technology, the Space Shuttle main engines, hydrogen engines, and did not have the thermal protection tiles either. So only for approach and landing tests. And then we had a total of 5 orbiters, but as you know, Challenger was lost in January 1986, was replaced by Endeavour, which you see here. So for a long time in the 90s, we had 4 orbiters, but we lost in 2003, February 2003, we lost Columbia. So at the end of the program in 2011, it was a total of 30-year program from 1981, the first flight, 2011, the last flight. We had 4 orbiters, but at the very end, we had only 3. And what was achieved, this is a summary, of course I'll detail all of this later, but a total of 135 missions, so way less than had been anticipated originally between 1981 and 2011. But it allowed 355 different astronauts and cosmonauts, because Russians were involved also, from 16 nations to fly in space. So a lot of people went to space thanks to the shuttle program. It was flying on the average 4, 5, 6 times per year, each time 7 crew members. And of course, many of them flew several times, like myself. I put here amazing capabilities and performance for LEO access and utilization, but expensive and quite dangerous. 2 major and fatal accidents. Again, Challenger in January 1986 and Columbia in February 2003. And that's not a very good ratio. 2 major accidents out of 135 flights. It wouldn't be very acceptable for civil aviation, for instance. Obviously. And this is really what darkened the program, these 2 major accidents. And they would have been avoidable. I'll come back to that without going into too much detail, but they would have been avoidable. That was a dark side of the program. And there's no doubt that a large winged space vehicle with a large thermal protection, which is very fragile and has to be in good shape, in good condition for the reentry, this is one dangerous aspect of a large winged spacecraft like the shuttle. But Americans had the courage to try it, to do it. And I have a lot of respect for the ones who said, we're going to do it and try it. That's the way to go. Finally, it was not really a totally successful program, but at least they had the courage to do it, to try it. Quite a technical and industrial achievement. We gained a lot of knowledge in this program. And the last point, that this is important, it made 2 major programs, a very successful program possible. The Hubble Space Telescope, I'll talk more about this later, and the International Space Station, which would not have been possible to be assembled in space without the Space Shuttle. That's a wonderful picture. I mean, we all here like airplanes and cockpits, and whenever I see this picture, I get emotional, I can tell you. This is a workspace for missions of typically 10, 11, 12 days on orbit. There was another compartment. This is the flight deck, and we had a mid-deck compartment where we had the kitchen, the restroom, a lot of lockers. We had the airlock, and this is the place where we were spending part of the time, but that's a cockpit. Very complex cockpit. And this is the glass cockpit that was installed on all orbiters around the year 2000. But originally we had electromechanical instrument, pretty much like the first 747s, DC-10. But they were replaced by glass cockpit, very, very well-designed glass cockpits around the year 2000. And as you see, very, very complex. I mean, there are switches and circuit breakers and instrument everywhere. This is the place of the commander with a rotational hand controller. It's basically a stick with 3 degrees of freedom, the roll, the pitch, and the yaw. Because on orbit, you don't want to use the pedals, the rudder. You want to use one controller for the 3 degrees of freedom rotation. And this little switch here, like a mushroom, black mushroom, is a translation hand controller. When you are in space, you have 6 degrees of freedom that you can manage. 3 degrees of freedom rotation, I mentioned them, and 3 degrees of freedom translation. This is 1, 4 aft, left, right, and up, down. Only available for the commander. The pilots or co-pilot didn't have that, only the rotation hand controller. But anyway, you will only use this when you were in space. This is for translations in the space environment. Central console, these are the keyboards to enter data into the computers, 5 general purpose computers. And the ceiling was full of switches also, mainly the switches to control the reaction control system. 38 small rocket engines in the nose compartment and in the tail to do all the maneuvering while on orbit. And you had switches that either had the position GPC, general purpose computer, controlling these valves, or you had manual close or open. Yeah. But you see also here, this is the systems managed by the co-pilot and system managed by the commander. Very complex cockpit. I mean, the vehicle in itself was extremely complex, and that's also one of the negative aspects of the shuttle. It was too complex. And the training was very extensive in order to be able to master all the phases of flight, the ascent, the on-orbit phase, the re-entry, approach, and landing in this environment was really very demanding. Now, this is a bird's eye view of the flight deck. I showed already this part here. You see the seats. They're not as comfortable as the seats in a Airbus airliner. You know, leather, soft cushions. It's military style, rustic and hard seats. And this is the so-called aft flight deck. During the on-orbit part of the mission, the shuttle could be flown from the aft flight deck. And most of the time, the crew was around there and not so much on the seats. There were 2 more seats that were installed here because if there were 7 crew members, which was the case for nearly all of the missions, you had the commander, the pilot, the flight engineer sitting between the commander and pilot, and there was number 4 behind the co-pilot. And there were 3 seats in the mid-deck for 3 crew members who had nothing to do for the ascent and entry. Ascent and entry was managed by these 4 crew members here. And this is the aft flight deck. Again, if you look in the -X direction, +X being towards the nose, with 2 windows that gave visual access of the crew to the payload bay, and you have 2 large overhead windows, very good optical quality. And you have here translation hand controller and rotation hand controller. This is to fly the orbiter, the shuttle. And for the robot arm, this is the control station for the robot arm operator. You have the same translation hand controller and rotation hand controller. Always the idea is to have on the right hand the rotation, on the left hand the translation. Like in a fighter where you have the throttle on the left hand and the stick on the right hand. And it's interesting because this is set at a 45 degree because you can decide whether you want to control it with respect to the -X body vector, which is to the tail, or to the -Z body vector, which was up. So you had a switch here where you decide whether the reference was -X or -Z. And of course, if you do the translation, if you select the -X, if you push on that 45 degree inclined plane, you're going to be going toward the tail. But if you select the -Z, which is up, if you push, you're going to go up, perpendicular to the plane of the wings. Yeah. A little trick. Yeah. Okay, a few words about the data processing system. DEEPS is for data processing system. The architecture for the ascent to orbit, on-orbit phase, and re-entry and landing. We had 5 similar computers. They were called GPCs, general purpose computers, mil-spec, built by IBM, derived from the B-1 bomber. And during the ascent to space and also the re-entry, out of these 5, you had the first 4, GPC 1 through 4, working with the same software as a redundant set and checking each other. If one of them was giving another solution than the 3 others, it was not automatically taken out, but the crew was informed. And it was up to the crew to take it down. The number 5, GPC 5, was from a hardware point of view exactly the same, but it was loaded with the software that could do the same, but designed and built by another manufacturer. So you had a protection against hardware failures with the first 4, which were the same, but loaded with the same software. So if you had one of them from a hardware point of view it didn't work, the crew could take it out. There was a protection against software failure that would have affected the first 4, the primary software, because they're running the same software. In this case, a big red button on the rotation hand controller. You engage the number 5, you take out the number 1 through 4, you engage the backup computer, and then you have only one computer, so you have no longer any redundancy from a hardware point of view, but at least you have a software that can take you home or take you to space. So this is the architecture of the database access system. That's a little detail that I gave, but I think it's interesting. This is the way they wanted to get protection against hardware failures and software failures. Okay, I explained this here. There was a huge effort by NASA and contractors to verify the absence of software bugs. We did not want to have any software bug that could cause an accident or the loss of the crew and the vehicle. Loss of the vehicle and the crew was similar because of the absence of a crew escape. And I was for 25 years in Houston from 1980 to 2005, and I spent 3 to 4 years as one of the crew members that was involved in SAIL, Shuttle Avionics Integration Lab. It looks like a simulator. It's not a simulator, it's a facility to verify the software. We had all the black boxes of the shuttle. We had a vehicle dynamics simulator. It had to be simulated in a computer. And then they were verifying the software prior to every mission. It was running 7 days a week, day and night, with the several shifts. The idea was to verify the software before every mission to be sure there was no glitch. And sometimes we found some glitches that were fixed before the mission. I spent quite a lot of time on this and I learned a lot. This was not formal training on the shuttle, but I learned a lot. It's something that was extra to training. In between period of training for flight, which took about 1 year for each mission, the mission itself, 10 to 12 days on orbit, and then debriefing for a few months. In between these periods, we were given a job assignment, and one of the jobs was to be one of the crew members in the cockpit of the SAIL facility to verify software. A good way to learn and to be involved also in engineering development activity. Now STS-1, the first shuttle flights, was in April 1981. In fact, it was exactly 20 years after the first flight of Gagarin, or the first flight in space of Yuri Gagarin. 12th of April 1961, the first human flight in space, one orbit around the Earth. And John Young and Bob Crippen were the crew members for the first shuttle flights, 12th of April 1981. By the way, John Young regrettably passed away about 2 weeks ago. For me, he was a giant. Probably the best astronaut that has ever existed. He flew twice on Gemini. He flew twice on Apollo. He was a commander of Apollo 16 in April 1972. And he was always telling me, he was a good friend of mine, always telling me, well, STS-1 is more dangerous than Apollo 16. Apollo 11 was a dangerous mission because it was the first time. But then we had Apollo 12, 13, we know it nearly ended in disaster, but the crew was saved. Then we had 14, 15, which went fine. 16, the system was well in place, but the first shuttle flight, which had never flown unmanned before, was a very dangerous mission. And this man, John Young, was the commander with Bob Crippen. I have an enormous respect for John Young and for his memory. Liftoff of STS-1, 12th of April 1981. On orbit, they discovered that there were missing tiles. You see here, this is the payload bay, seen from these windows in the outer cockpits. And these are pods containing fuel for the on-orbit attitude control system, and also for the so-called OMS engine, allowing the deorbit burn, the deceleration for the reentry into the atmosphere. And there were some missing tiles, and the big concern was, do we have any missing tiles in the bottom of the orbiter? And there was no way to check that. But I remember when John and Cripp reported that they had missing tiles, and they could not downlink this picture. This was brought, it was of course, it was not digital camera, it was a normal camera, and this picture was brought back to Earth. But they were describing it, and people were really concerned. And I remember that re-entry 2 days after the ascent, or the 14th of April 1981, people were really anxious. went fine, and it ended up with a landing at Edwards Air Force Base on the dry lake, not on a runway. We wanted to have this huge surface, about 25 kilometers long, to be sure that we were okay. Being a little bit too low energy or too high energy would have been okay because such a large surface. Yeah. A lot of guts. John Young, Bob Crippen. Just a few words about the ascent of the shuttle. This is not the scale, but there were basically 3 abort modes. The normal ascent was after 2 minutes separation of the boosters, you continue until main engine cutoff, 8.5 minutes after liftoff. Then the separation of the tank was falling down in the Pacific Ocean. Then there was sometimes the OMS maneuver using the orbital maneuvering system engine in the back with autonomous fuel, not oxygen hydrogen, because this is separated and there was no more fuel anyway then. In fact, at main engine cutoff, we had normally about 1% of fuel remaining in the tank. So everything is calculated precisely, but not with a large margin. 1% still meant 7 tons of liquid oxygen hydrogen, but it was giving only a couple of seconds of extra burn. And that's a nominal mission. Then, of course, this is not the scale. You have to imagine you're on an orbit at the apogee of that elliptical orbit on the other side of the Earth. You give another delta V, another acceleration to circularize at the apogee, typically 300 kilometers altitude. Now, if we had one of the hydrogen engine failure relatively early, like 30 seconds after liftoff, we could never get to orbit, not even go across the Atlantic Ocean. We had to do a return to launch site. And you see here the return to launch site. 20 minutes after liftoff, there was a landing on the runway, 5-kilometer runway at Kennedy Space Center, Florida. Another mode that is not expressed here is the TAL, transatlantic landing. There was a window of loss of an engine between about 2 and 6 minutes after liftoff. You could not even get to orbit, but you were going through the Atlantic, either with a landing in Africa if it was a low inclination orbit, or in Spain if it was a high inclination orbit. And then the AOA was thought about, but it was never trained much. It's orbit once around. You do just one orbit and you go and land at Edwards after a little bit less than an orbit. You lift off on the east coast of the US and you land on the west coast after a little bit less than an orbit. And then there's the ATO, abort to orbit. If you lose one of the engine relatively late in the ascent, like 1 minute before the nominal main engine cutoff, you can get to orbit, but it may be a somewhat lower orbit than the one that you had planned. So all of these aborts were very much trained. Most of the training sessions for the ascent ended up with an abort. Because if the ascent was nominal, there was nothing to do. It was hands off. So to train the crew, we did a lot of abort landing, which sometimes ended up in LOS, in LOC, sorry, loss of control. Now, in order to initiate the abort, it was a very simple operation. You had a button here. It was normally the off position. RTLS is return to launch site. ATO is abort to orbit, and TAL is transatlantic landing. So you rotate the button to the position you want, and you push on this button here, and here we go, load all the software to do the abort mode. So very simple user interface, but dramatic consequences, obviously. It was never used except once we had abort to orbit, when we had a one engine failure on Space Lab 2. It was in 1985 or so. But relatively late, we have one engine failure, and they reach only a somewhat low orbit than anticipated. But we never had to use any of the other abort mode. The most critical ones would have been return to launch site, or TAL. Imagine you lift off from Kennedy Space Center, and 20 minutes later you land in Kinshasa with the shuttle. It's not obvious. Trained a lot, but never used. Okay, let me describe what we see next. We'll see a short video of, that NASA produced relatively recently, liftoff of the Space Shuttle and ascent for the so-called first stage until separation of the two solid rocket boosters 2 minutes after liftoff. It's very, very nice video, very emotional. You can hear all the conversation. This is, of course, a very critical time, the few minutes before liftoff, to be sure that everything is okay. In the flight control room in Houston, you can hear the flight director who is asking everyone if they are ready to go. And you can hear the go from each of the positions. If everyone is go and the crew is go, then it happens, and it will happen in the video here. Let's go. Can we turn off the lights maybe a little bit? I don't know if it's easy to do.
T-minus 90 seconds and counting. All systems are go. We're about 90 seconds into launch of Space Shuttle Discovery. T-minus 60 seconds and counting. We're transferring to orbiter internal power at this time. Discovery is now running off its 3 onboard fuel cells. Coming up on a note for auto sequence start.
These are the 3 hydrogen engines. Each of them about 300 tons of thrust, so about 1,000 for the 3. And produce 1.5 tons of water per second. So that this is green power. The crew is here, 7 people in the cockpit.
2, 1. Discovery's onboard computers commanding the main engine nozzles to swivel, aiming the shuttle for its precise target in space for main engine cutoff.
What a machine. As mentioned, you have main engine cutoff 8.5 minutes after liftoff, separation of the tank 18 seconds later, and the tank has, of course, initially the same velocity vector as the orbiter, but it's very large, it's very light. So it has a so-called small ballistic coefficient, and with the drag in the remaining atmosphere, we were at main engine cutoff at about 120 kilometers. There's still some atmosphere, there's still some drag, but the orbiter had not enough drag to come down in the Pacific Ocean, fortunately. Everything was designed so that it was going up to the apogee of the orbit on the other side of the Earth, then it was circular rising. But the tank after separation was rapidly coming down and falling down in the Pacific Ocean about 45 minutes after liftoff. You see here the tank after separation. And here we are on orbit. Of course, a lot of work to do once we get there. We needed to load the computers with the in-orbit flight software, because the computers had very little capacity, and there was the software for the Ascent, but the software was useless during the on-orbit phase, so we had to load in the memory of the computers new software for the on-orbit phase, and before the re-entry, we had to load again the computers with the new software for the entry. You can imagine the stress there, because if you can't load them, of course we had several of these computers, we had a lot of redundancy, but still it was always worrisome to have to reload computers with the software corresponding to the phase of the mission. And then we have to open the payload bay doors, exposing the content of the payload bay to the space environment. But you see the incredible view you have. This is over the ocean. This is a so-called terminator that limits day-night on the surface of the Earth. It's day here. On the other side, it's night. And every 45 minutes, you cross the terminator because you go around the Earth in an hour and a half, or 16 times around the Earth in a terrestrial day. Velocity 28,000 kilometers an hour, or about 7.7 kilometers per second. And of course, this is not a chosen velocity. It has to be this velocity because these are the laws of mechanics. And for every altitude, you have a certain velocity for circular orbits. And the circular velocity goes as 1 divided by the square root of the distance to the center of the Earth. So the further away you are, the slower the velocity, but it's very high at low Earth orbit. Nice picture of the shuttle taken from satellites, a German satellite, Space, on mission number 7 of the Space Shuttle, 1984. The satellite was separated from the orbiter using the robot arm, which you see here, and you have the crew looking at the satellite through the overhead windows here. And they took a picture of themselves, like a selfie, with a Hasselblad camera that was installed in the satellite. And it's a beautiful picture. It shows also the characteristics of the environment in low Earth orbit. The sky is completely black. As long as the sun is above the horizon, you don't see the stars on the planet in the sky because the eyes are on the day mode and they don't have the sensitivity to see the faint object like stars. So the sky is completely black, and you can see this here on this picture. And the Earth has the dominant colors of blue and white, of course, for blue for the oceans, white for the clouds. You have to imagine that you follow the orbiter from this satellite. The velocity vector is inside the screen with 7.7 kilometers per second. What a privileged position for a human being. It's really, really wonderful. Reentry, I happen to have this position as a flight engineer for my second flight, the first servicing mission of Hubble in December 93, sitting between the commander on the left and the co-pilot on the right. This is still not the glass cockpit, but this is the old instrument panel. And this is a night re-entry. The idea for the re-entry is you give a little braking impulse, we call it delta V, change in velocity, on the opposite side of the Earth from where you want to land. So it was over the Indian Ocean for landing at Kennedy Space Center. Very, very small braking action, and then you come on an elliptical orbit that will intercept the atmosphere after an arc, which is still in weightlessness. At some point during this arc, you will encounter the atmosphere. Then it ends up with a reduction of the angle of attack and the transition into a gliding vehicle. But during the hot phase of the reentry, between about 80 kilometers altitude and 50, it's very hot outside. And although it was a night reentry, you see outside it's very bright because of the high temperature of the plasma outside of their spaceship. It's like if you were in an oven, but the temperature inside the spaceship was completely nominal, 23, 24 degrees or so. Again, a huge technical challenge to achieve that. This is a scene from outside. You have 7 people who are living in this fireball here. Don't want to go into too many details here, but these are some parameters for the reentry. This is the time from crossing the so-called entry interface. Entry interface was 400,000 feet. So the altitude, 400,000 feet, or about 120 kilometers. This is the time when we considered that we're re-entering the atmosphere. So this is the time from the entry into this is the altitude, 40,000 feet coming down. And you have here the angle of attack was maintained at 40 degrees nose high and maintained pretty precisely until the time you were getting to 1.5 G deceleration. Then the idea was to decrease the angle of attack to never exceed 1.5 G deceleration, which is a very small number. If you consider the reentry of the Soyuz, they got 4 to 5 G deceleration. But with the capability to do braking at the high layers of the atmosphere with the exposure of this huge surface of the wing in the high layers, you were braking enough that when you were getting to the lower layers, higher density, you were slow enough, you did not have a lot of deceleration. And this is the hot part of the velocity here, hot part of the entry between about 80 kilometers altitude and 50 kilometers altitude. For about 10 minutes, you had this very high temperature, and during a night re-entry, it was completely bright outside. Now, when you're getting close to the runway, you had the so-called TAEM, Terminal Area Energy Management. The idea, because you did not have any more engines for approach and landing, the idea is to always come with an excess of energy, like when they come with a glider. And then use methods in order to kill that energy so that eventually you are at the threshold of the runway at the proper altitude, of proper velocity. To dissipate energy, we were doing S-turn in this area prior to come overhead. This is a runway here. The idea is to land in this direction. And most of the time, we chose a so-called overhead approach. We come over the runway, then we come and come on the surface of this heading alignment circle, H or cylinder, heading alignment cylinder here. This was about 15 kilometers altitude above the runway, passing through Mach 1. And after passing through Mach 1 from high numbers to low numbers, the crew was taking control manually, the commander. And this whole end of downwind, we can say, and base turn and final approach was done manually. No autoland capability. For all the 135 missions, -2, because we had 2 accidents, of course. But for the 133 that landed, it was landed manually by the commander. And then we come with the so-called steep glide slope, about 20 degrees. We had a pre-flare at about 2,000 feet altitude in order to come to a shallow glide slope, only 1.5 degrees glide angle, which of course is much less than the stable glide. So the angle of attack had to be increased in order to maintain the lift during that shallow glide slope. But it was taking the orbiter on a straight line all the way to touchdown at about 200 knots. The steep glide slope was done at 300 knots. And the air brake was partly open. If the spaceship was a little bit too high, the crew had only to push down on the stick, and the air brake was deploying more. It was a split rudder in order to maintain the 380 knot. If they were a little bit too low, they were taking the nose up a little bit, and then the air brake was closing, and they could, approximating the speed, they could rejoin the proper glide slope. So energy management was done with S-turn here, and coming back with also too much energy, but speed brake partly deployed, steep glide slope, pre-flare, final glide slope, and there was practically no final flare. If you come with 1.5 degrees, it gives you a reasonable rate of descent for touchdown at about 200 knots. Now, we had a lot of displays, and the displays were not very user-friendly. Unlike what you have now in modern airliners or in fighters, it was not very user. Here you have the horizontal situation, you have the orbiter, and you have predictors, 20 seconds, 40 seconds, and 1 minute. If you maintain the attitude or the orientation, which means rotational hand control in the center, you maintain all the parameters, the pitch angle and the roll angle. Then that's where you will be in 20 seconds, 40 seconds, 60 seconds. This is unrealistic. You would never do that. If you land here, this is the heading alignment cylinder. You would come normally from there, here, and you do this, but you go via overhead the runway. And if you wanted to change parameters, this is Vandenberg, the VBG. This is a selection of the runway 12 or runway 30 at Vandenberg. You could manipulate the TAEM. You had TACANs and a microwave landing system at that time. We had no GPS initially. Now, there was a head-up display. This is not the head-up display of the shuttle, but it was a shuttle trainer aircraft, the STA, which is a modified Gulfstream II that was equipped on the left-hand side for training of the astronauts with a head-up display exactly like the shuttle. And on the right-hand side, we had an instructor. And there was a big switch in the middle. It was either the Gulfstream II normal or it was the shuttle simulator. And when it was the shuttle simulator, it was the astronaut training. And of course, Gulfstream II has much less drag than the shuttle orbiter. So there was in-flight reverse capability in order to emulate the drag that the orbiter would have. With the Gulfstream II, if you put the nose down, 40 degrees nose down, the velocity will be far too high. But you had speed brakes on one hand, the landing gear was deployed, and there was in-flight reverse capability. But that's what you had on the head-up display. You have the normal indication, like the position of the speed brake, the altitude, the speed, and you had the runway, synthetic runway displayed on the head-up display, which was superimposed with the normal runway if everything was going well. If the weather was not too good, then you could have an indication where the runway was, and when you were coming in clear air, then you would have a match of the synthetic and the actual runway. Landing, again 200 knots, a big brake chute in order to reduce roll distance. But the runway 5 kilometers long, so it was plenty. Now, of course, all of this was monitored from Mission Control Center in Houston. You see here approach to runway 15 at Kennedy Space Center. Again, the shuttle is coming from there, overhead, and is coming on the surface of the heading alignment cylinder until it's aligned with the runway for landing. Briefly, the G values, acceleration values for the ascent and the entry. Now, this is 0G here, and you have to, they put the negative numbers here, I don't know why, but you start with about a G.5 only at liftoff, because you are so massive, about 2,000 tons, and the thrust is 3,000 tons, so it's a factor 1.5. You have about 1.5 G at liftoff. When you go through maximum Q, maximum dynamic pressure, there was a reduction of the thrust of the boosters and of the Space Shuttle main engine in order not to exceed the max Q for the vehicle. Here you have solid rocket booster separation. You were at about a little more than 2 Gs. You go rapidly to about 1 G. Suddenly you have much less weight, but much less thrust. And then you have only the main engines, and the Gs increase until you get 3G, which is the design limit of the shuttle, plus, of course, some margin. And you are maintaining the 3G longitudinal acceleration. It's not the 3G you have when you make a tight turn with a fighter. It's longitudinal. It's every second you add 30 meters per second to your velocity for the last minute, which allows you to reach this very high velocity. But you see it's quite benign acceleration profile on ascent. And on entry, you go, as I mentioned, to only a G.5. and then you reduce, and then you have a normal flight like an airplane at 1G, except during the heading alignment circle or the base turn, where you have, of course, maybe 1.5 up to 2G if you have 60 degrees of bank. The biggest challenge of the shuttle program was really the main engine and thermal protection. The main engine, again, worked fine, but from a technical point of view, these so-called cryogenic engine, oxygen, hydrogen, producing water and thrust, were technically very difficult. If you look at what SpaceX does, they don't use cryogenic engines, far too expensive and difficult. So this is a kind of a technical development that can be done by government agencies like NASA. They spent a lot of money on this, but at least they developed very reliable cryogenic engines. The commercial company, they use kerosene and liquid oxygen, much cheaper. Thermal protection was, of course, also a big problem. It was fatal for the Columbia orbiter on the 1st of February 2003 because of the damage in the thermal protection system. The vehicle was destroyed and the crew was killed. I don't want to go into the detail of that, but just to tell you that in the Space Shuttle main engine, you had pre-burning of the hydrogen comes here, liquid form, the oxygen here, pre-burning in high-pressure turbopumps, and then you have going to the combustion chamber here. You have the results of this pre-burning with much richer in hydrogen than in oxygen for the normal mixing ratio that you should have. So you have essentially hydrogen coming here with a flux of oxygen, and as you saw on the movie, you have an ignition system that produces the combustion here and the thrust through the nozzle. But it's pre-burning of the hydrogen in the high-pressure turbopumps. That's a test of the Space Shuttle main engine. Again, it was a huge development cost, but a very significant development in technology in this area. Now, thermal protection system, you see here the detail of the tiles. This is the Space Shuttle Atlantis, which is exposed at Kennedy Space Center, Florida. You see all of the mark of the high angle of attack during entry. You can nearly see the 40-degree angle of attack. These are the nozzles for the forward reaction control system. The down-firing rocket engines were on top of the fuselage. It didn't want to have anything at the bottom because it was exposed to the ram air hypersonic during the reentry. It didn't want to have it was on the top, but it was just canted. Each individual tiles, and many of them were similar, but there were a lot of them which were dissimilar, which could only be used in one location. So it meant a very, very high cost. This is in the orbiter processing facility after landing. During the several months of processing of the orbiter, there were a lot of these tiles that were replaced very, very carefully. It was a lot of manual work that had to be done very, very, very well. This was a significant element in the cost of the utilization of the Space Shuttle. Some highlight, I'll describe some missions, but very briefly, just so that you can see the variety of missions that you had, the large spectrum utilization of the shuttle. The Europeans had interest in Space Lab. This was the contribution of the European Space Agency to the shuttle program. That's the reason why Europeans could become astronauts, with the selection in 1978 of the first three, Ulf Merbold from Germany, Hugo Ockelt from the Netherlands, and myself. This was something that NASA offered in exchange for the delivery of this laboratory. Installed in the payload bay of the shuttle, and allowed the utilization of the shuttle like a mini space station for a period of up to 15 days. That's Ulf Merbold, the first ESA astronaut that flew on the shuttle as a payload specialist. Now, this is a great picture. NASA developed a manned maneuvering unit, which is a small personal vehicle allowing astronauts in spacewalking to take that vehicle in the payload bay and then move away from the shuttle. This is Bruce McCandless, who also passed away a few months ago. Very, very brilliant NASA astronaut. he did the flight testing of the manned maneuvering unit. So he moved away a few hundred meters away from the shuttle without safety tether. And he's flying formation with the shuttle with his little space vehicle at 28,000 kilometers an hour. This is a wonderful picture. This is a human spaceflight at its best. But of course, he cannot re-enter the atmosphere with his spaceship. He needs to go back to the shuttle. Now, the manned maneuvering unit was not used very much. It was never used for Hubble, for instance, but it was used to recover satellites. Satellite is slowly rotating. They came with a manned maneuvering unit. They docked to the satellite. They used the attitude control system of the manned maneuvering unit to break the rotation of the satellite and brought it back to the payload bay and to Earth. I'm just showing these few pictures to illustrate the enormous flexibility of the utilization of the shuttle. Unfortunately, two major accidents. I won't go into the detail of these. They would have been avoidable. There were problems with the O-rings of the solid rocket boosters that were noted already before the Challenger accident. That morning, it was very cold. The O-rings didn't perform their function. The design of the joint between the segment of the solid rocket booster was not very good either. And the combination of these two and the decision to launch in low temperature, which was the major cause of the accident, led to this fatal accident 73 seconds after liftoff. And we lost Columbia in February 2003. The problem was that a piece of thermal protection of the external tank detached during ascent hit the leading edge of the left wing, made a hole, but was not detected. And NASA saw that but from below, that piece had detached from the external tank. They thought that because it's basically very low density styrofoam, they thought there would be no damage, but in fact there was damage. It was fatal during the re-entry of Columbia 2 weeks later. And you see here over Dallas, the pieces of Columbia coming back down to Earth through the atmosphere. One of them is a crew compartment. Now the shuttle was essential for International Space Station assembly. This is a very nice picture at night taken from ISS, International Space Station, where you see the shuttle docked to it, bringing a new element. This is a MPLM from Italy. This is the robot arm of the shuttle. There's a robot arm of the station, and these two robots' arms were used to take the piece from the payload bay of the shuttle, install it on the existing part of the station in order to perform the assembly until 2011. NASA decided not to fly one single shuttle flight beyond the end of the assembly of the International Space Station. And the reason is, as I mentioned before, cost and danger. They didn't want to have another accident. And that's 2011. I don't know whether it's flight 135 or 134, but this was taken from Soyuz. This is the Russian segment. This is a US segment with the European lab, Columbus here, the Japanese lab, the big solar arrays. And at that time, the crew came back using the Soyuz, which attached in the Russian segment. They came a little bit on the side. They took that very nice picture of the shuttle attached to the International Space Station. The shuttle was always, the station is moving to the left, always docking to the forward portion of the station. And the Russian modules, whether it was Progress, resupply vehicle, or Soyuz, were docking to the rear part. This is the ATV, Automatic Transfer Vehicle, resupply vehicle from the European Space Agency. Now that's the final landing of Atlantis, STS-135, July 21st, 2011. Again, no mission after the last assembly mission of the International Space Station. This was a very emotional moment. The shuttle was a big program. It was technically very hard, operationally very difficult also. And Edith Disday, a lot of people lost their job after that. Yeah. These are steps in my life, but very briefly, I was an astrophysicist training, studying physics in Lausanne and astrophysics in Geneva. A lot of stays in the Gornergrat Observatory near Zermatt in Switzerland, where we're getting photometric data of stars analyzed in Geneva. in parallel with that, because in Switzerland we have this militia system where all the males are supposed to be part of the defense system, whether they are bakers or lawyers or dentists, so they have to spend a certain fraction of their time in the military. I chose to be in the Air Force and was accepted as a pilot, trained as a pilot, interrupted my studies for 2 years to become a fighter pilot flying Venoms first, and then the big step was a transition to the Hawker Hunter, a wonderful airplane. I fell in love with this airplane, and I flew it for about 22 years, about 6 weeks per year. Every 2 months, we had a 1-week training in some of our war airfields. We used it as a ground attack airplane, not as a fighter. And that's a picture taken from a 2-seater, the kind of landing strip we have in the Alps. We had about 10 such landing strips in the Alps. We phased them out now because this is a Cold War preparation in a way. But landing 10-ton jets, the Hawker Hunter, on these small 2-kilometer-long runways was not an easy thing. And of course, the topography was making it even difficult. But it was a challenge that we appreciated. I loved flying the Hunter for 22 years in the Swiss Air Force. I flew the F-5E Tiger after that, but it was not like the Hunter. It was like a normal airplane, the Tiger, but the Hunter was a wonderful airplane. Selection as an ESA astronaut in 1978, the first group, Ulf Merbold from Germany, Bubo Ockels and myself. And we were sent to Houston, training in Houston. My colleagues, Ockels and Merbold, came back to prepare the first Spacelab mission, which happened to be STS-9, the 9th shuttle flight. John Young was a commander for that mission. But I stayed in Houston for 25 years to train fully on the Space Shuttle as a so-called mission specialist. I was the first non-American to do that. These are the 4 missions that I flew, 1, 2, 3, 4. And this is the first flight, STS-46, the 46th shuttle mission in 1992. This is the crew, Lauren Schreiber, the commander, Marsha Ivins, American woman astronaut. You see her long hair. This picture was really taken in space, not in the studio in Houston. The first Italian astronauts, Franco Malerba, because we had Italian payload on board. The purpose was to deploy Eureka, European Retrieval Carrier, a small scientific platform of the European Space Agency. We deployed it to orbit. Then we tested TSS, Tethered Satellite System. This was the Italian component, which was a satellite at the end of a leech, at the end of a cable, conducting cable, electrically conducting. You can imagine if you have an electrical conductor moving rapidly through the geomagnetic field, you'll generate voltage. And you generate also a current if you can close the circuit, which we did through the ionosphere. Quite interesting. I could give a lecture on this one. It was really interesting. It didn't work too well, but it was really interesting from a physical point of view. You can imagine if you have a satellite at the end of the tether, you can have all kinds of problems if the tether becomes slack. As long as it's taut, it's okay. If it becomes slack, it can be a problem. And we had a lot of training about how to handle slack tether. And in addition to the official crew picture, we took this one to express our worries about slack tether. This is Commander Lauren Schreiber, Marsha Ivins, Franco Malerba, Jeff Hoffman, Franklin Chang Diaz, Andy Allen, and I'm here, and I'm strangled by the tether around my neck. They always told us, do your job seriously, but don't take yourself seriously. And you can see that here. I had 2 tether satellite missions, and number 1, number 3, and number 2 and 4 were a visit to the Hubble Space Telescope. A wonderful instrument for astrophysics, on orbit around the Earth, 28-degree inclination, 600 kilometers altitude. Cooperation project between ESA and NASA. A relatively small telescope. It fitted inside the payload bay of the shuttle, but it means that the primary mirror had to be relatively small. In fact, 2.4 meter diameter primary mirror here. This is the optical part of the Hubble. This is the instrument part, solar rays, antennas to command the telescope and send back the scientific data. We had a problem because it was launched in April 1990. It happened that the primary mirror didn't have exactly the right shape. So the first servicing mission, which was planned for end of 93 or 3.5 years after deployment of the satellite on orbit, the main objective was to install the optical corrector, do a few other maintenance tasks, but mainly correct the optics. This is the deployment of Hubble in April 1990. At that time, we thought this is going to be wonderful. And then a few weeks later, when they took pictures of the first star, they realized that it was not getting sharp pictures, so we needed to correct that. These are all the servicing missions, servicing mission 1 through 4. This is shortly before the retirement of the shuttle. Hubble works fine now, thanks to the work done on the last servicing mission, but also on the previous ones. I was part of the number 1 and the number 3, which was my last mission in December 1999. Great picture taken 600 kilometers over Australia during servicing mission 1, or STS-61. I was a robot arm operator and a flight engineer on board. This is the telescope, which we had made a rendezvous with, grappled with the robot arm, installed in the payload bay. Then we did 5 spacewalks. Bang, 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 very, very precisely executed like training to fix install the optical corrector, change the solar rays, which we did on the number 5, which is recorded here. And we did a few other things like add memory to the computers, change the battery, change gyroscopes also. But this is a great picture. What a wonderful working space. 600 kilometers above Australia. You see the southern coast of Australia with Adelaide and Antarctica in the background. That's Story Musgrave and Jeff Hoffman here. Spacewalk number 5 out of 5. Wonderful memories. That's a crew, a happy crew. Because we had, this is after 5 spacewalks had been done. You see the telescope is still attached to us in the payload bay. We had exchanged the solar rays. And this is the aft cockpit, you recognize it. This is a translation hand controller for the robot arm. We had the same for the shuttle behind the shoulder, Story Musgrave. Commander Dick Cavey, Jeff Hoffman, Ken Bowersox, Tom Akers, Katie Thornton, Story Musgrave, the most experienced astronaut at NASA. And for me, a huge privilege to be part of that crew. And I remember a few weeks after we came back, we had the first picture. This is a picture of a Messier 100 galaxy before the fix, and this is after the optical fix. Because during the mission itself, we could not verify that the optical correction was good. This was done after the telescope was detached, commanded by the ground, pointed to a star or to a galaxy. And for us, it was a huge reward to see these pictures a few weeks after the end of our mission. Since that time, Hubble has been a wonderfully productive scientific instrument. And for us, this was in the middle of 1994, so about 6 months after our mission. For the first time, they did the Hubble Deep Field. Imagine a relatively small, in fact, a very small, L-shaped window in the constellation Big Dipper, Ursa Major, La Grande Ourse. About 2 arc minutes by 2 arc minutes. This is 1/15 of the diameter of the full moon. There was nothing there, seen from the ground. After 10 days of exposure with Hubble, we see hundreds of galaxies. And you can imagine for us, of course, we were not the only one who had contributed to fix Hubble, because the people who had developed and built the optical corrector, this is a very difficult task, but we were part of giving a capability of Hubble to obtain results which you cannot obtain with a telescope based on the ground, because you need a 10-day exposure with extremely precise pointing, 7,000 of an arc second pointing accuracy. And it could maintain that accuracy during 10 days. That's a wonderful result. And very faint galaxies. This is a star here. That's a star. Every object that has cross, there's another one here, is in the foreground. All the other objects are galaxies, up to a distance of about 10 billion light years away. For us, this is the reward. It was a difficult mission, it was risky, but this is the reward, and a wonderful reward. This is the third mission, very briefly, another tethered satellite mission with two Italian astronauts, Maurizio Cheli and Umberto Guidoni. Again, we had Jeff Hoffman and Franklin Chang-Diaz, because the one who knew about tethered satellite dynamics, they were reassigned to this mission. And this is the last breakfast before we go to the launch pad for launch. It is always a little bit ceremonial. And again, we tested the tethered satellite. It worked much better than the first time, but still it was not a total success. In fact, the tether broke at 19.6 kilometers. We lost the satellite and the tether. And if you look at Google STS-75 or TSS-1R, R for repeat, you see that there is a STS-75 conspiracy, because we had some pictures with a camera that was not focus adjusted. And you have big blobs like this. Sometimes you had pieces detaching to the payload bay and illuminated by the sun, and they were quite bright. And if the camera is not adjusted to take a picture of that object, it's blurred, and it gives you a big disk on the camera. And people pretended that we had seen a UFO, and we had never officially said that we had seen one. And NASA was hiding the fact that STS-75 had been visited by extraterrestrial, and we were visited by this UFO. So look at Google STS-75 UFO conspiracy. We are supposed to have been lying to the people because we were visited by UFO who didn't say anything. Anyway, last mission, another mission to Hubble, 6 years after my first one. First one was December 93, December 99 was STS-103. This time I was one of the spacewalking crew member training in a big water tank with a very precise model of Hubble. We had this time to exchange gyroscopes, one pointing camera, and the main computer of Hubble. These were the three tasks. Here we are again over Australia. I'm here inserting the new pointing camera, fine guidance sensor number 2. This is the old one that was defective. I had removed it, put it in the payload bay on the side temporarily before I was going to put it in the thermostabilized container to bring it back to the Earth. And I'm installing the new one, helped by Mike Fowle, my colleague. He's climbing on the north face of Hubble here. Again, these Hubble missions were wonderful. And for somebody who had been an astrophysicist, to be able to work on Hubble and touch it was an incredible feeling. Here we are. I'm taking from a thermostabilized container the new computer of Hubble that Mike Fowle and myself installed on the telescope. You see that I have my head down. This is a reflection of the Earth on the visor of my helmet. So I had my head down, my feet in the payload bay, but down is always, the perception of down is where your feet are. So I had no problem looking up and seeing the Earth upside down. Down was where my feet were. A lot of people are surprised because I have the American flag here, and I should have had the Swiss flag. When Thomas Pesquet flew, of course, he had the French flag. That's quite normal. In fact, to tell you the truth, we asked for it, but we asked too late. It was less than 2 months before the mission, and NASA said, "Oh, it's too late because there's a lot of documentation needed to change that that part of the spaceship." For me, it didn't matter really, but a lot of my compatriots in Switzerland say, "Hey, Claude, you didn't want to have the Swiss flag on your shoulder." I would have liked to, but I didn't have it because we asked too late. Just a little detail. Oh, another thing here. We were 8 hours out on this spacewalk. So we went 5 times around the Earth. So it's day, night, day, night, day, night, day, night. And during the night, we continued working, illuminating the place of work with this floodlight. We always had a warning 1 minute before sunset, because it's day, 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 day. Suddenly in 20 seconds, it's night. So 1 minute before sunset, we turned on the light so we wouldn't be surprised by darkness suddenly. Here we are exchanging the main computer of Hubble, and here each astronaut is identified with the markings on the legs. This is Mike Fowle, the big red marks, and the little chevron. So if somebody floats away without having attached properly his safety tether, I have my safety tether here, you see. then we know if it's Mike or Claude. And we can decide if we go rescue him or not. Life support system for about 8 hours outside, or 8.5 hours outside. We were nearly at the limit with 8 hours and 10 minutes outside. We spent Christmas in space. In fact, the deploy day of Hubble after the repair was on Christmas Day, 25th of December 1999. So this is a nice crew picture of the STS-103 crew on Christmas Day, and we released Hubble. It was always an emotional moment. We had an attachment to Hubble. I have a big attachment to the Hunter, but I have a big attachment to Hubble also. Hunter I can still see. In Switzerland we have a few flying as civilian airplane, but Hubble is far away. But I still have a lot of attachment to it. Okay, I'm nearly at the end. I want to talk about some safety consideration of the shuttle. I mentioned that already. One of the major hazards of the shuttle, which caused, in fact, the last accident of Columbia in February 2003, was a fragile, exposed and fragile thermal protection system. If you have a capsule, the thermal protection for the reentry is protected during ascent. It cannot be damaged in any manner. A shuttle was a huge thermal protection that was totally exposed. The extreme complexity, this is a summary. I've mentioned these things already. The extreme complexity of the shuttle was also a risk factor and required extensive crew training. Now, in the design of the shuttle, you always have to have some rules for the design. And the idea was to have two failure tolerance and fail operational fail safe. If you have a redundant system like inertial measurement unit, you have 3. If you lose one, you can still do the mission. If you lose 2, you have 1 remaining, you can still save yourself. So that's what they mean by fail operational fail safe. If you lose all 3, you're dead. And one of the other guidelines was no single crew error could result in a catastrophic event. A catastrophic event is defined as losing the vehicle and the crew, the two together, because no escape system, if you lose the vehicle, you lose the crew also. There was a very thick document. It was not electronic at that time. It was in the 80s. The failure mode and effect analysis. NASA looked at all of the failures that could occur and what was a mitigating factor in order to avoid having a loss of crew, loss of the vehicle, in this case, FMEA. Now, as mentioned, there was no crew escape system, although after the Challenger accident, everyone had a parachute, which would give us a possibility, a crew escape in a small part of the spectrum of accident with the shuttle. If you lose engine and you end up in gliding over the Atlantic Ocean, you can pyrotechnically jettison the side hatch and come down with a parachute. But any explosive event, of course, if you have a parachute, doesn't help. But the absence of crew escape system after STS-5, STS-1 through 4, which were the test flights, the crew, like John Young and Bob Crippen on STS-1, had ejection seats, which was allowing crew escape in a small part of the ascent, the early part of the ascent. If you have a Mach 11 at 50 kilometers altitude, it was not even a capsulated seat. It was a normal ejection seat. But the absence of a crew escape system after STS-5 was a mistake, and NASA confessed it. But the price would have been too high. To do a modification of all the orbiters to have crew escape for all the crew members up to 7 would have been so costly, they decided not to do it and take the risk. A last reflection on the shuttle program. And this is quite an interesting statement by Michael Griffin, who was a NASA administrator from 2005 and 2009. And I read it slowly. If it is true that satisfaction equals results minus expectation, and if ultimately we have been unsatisfied with the shuttle program, maybe where we went wrong was not with the performance achieved, but with the goals that were set. This idea that satisfaction in the program is results minus expectations, I think is quite a good idea. There was such huge expectation for the shuttle, low price, access to space, and regular access to space, very frequent access to space, airliner type operation. This is a huge expectation. And the shuttle program was finally successful in the sense that it allowed, again, Hubble, the International Space Station, allowed so many people to go into space. But the expectation was so high that if you could take the results minus expectation, you get a negative number. So we can consider that the shuttle was not a totally successful program. I think this is a good formula. This is valid, of course, for all programs, all aerospace programs. Okay, I'm at the end. Thank you, I've been long. Thank you for your attention. This is a nice picture of the last wheel stop. The shuttle landed, then at some point the ground, because they are monitoring all the planes, were saying wheel stop. And this is the last wheel stop of the shuttle on the Ronald Kennedy Space Center in July 2011. And this is emotional for a lot of people. That's why I put a sniff here. Thank you for your attention.